For those of you who joined us, we'll go ahead and begin. Welcome to the Rescale and Next Limit Technologies webinar, XFlow 2016 in the Cloud with Rescale. I'm Sarah Dietz, the Business Development Manager at Rescale, and joining me today is Moyanto Port, our VP of Engineering, and Rudy Briano, the XFlow Lead Application Engineer. We're about to get started. A few housekeeping items first. We're recording and we'll be distributing this webinar later this week. If you have any questions during the webinar, please make sure to type them in the questions section in the GoToWebinar panel, and we'll address these later on. Here's our agenda for today. I'll start with a quick overview of the Rescale platform and the partnership we have with NextLimit. I'll then be passing this over to Rudy, who will introduce XFlow and will highlight their newest version, XFlow 2016. He'll also explain the model we'll be looking at today. Moyanto will then take over and go through a live demonstration showing how to set up, run, monitor, and post-process your XFlow simulations on the Rescale platform. He'll also demonstrate our DOE framework. We'll end with some time for questions. So let's get started. Rescale provides a comprehensive cloud HPC platform for running simulations. There are several key elements to the Rescale platform. The first is an intuitive interface that enables engineers and scientists to set up and execute different types of simulations with an easy-to-use workflow. The next component is software. We support a wide range of over 160 different software packages that are pre-installed and tested so that our users have one unified platform to execute all of their simulation work. The next key feature of the platform is our range of hardware. Rescale is a multi-cloud solution. We partner with several different infrastructure providers globally, accessing over 36 data centers, allowing our users to leverage a wide range of different types of hardware, including InfiniBand and GPUs. As mentioned, and as will shortly be demonstrated, Rescale's platform is straightforward and easy to use. Users can monitor their simulations and results in real time and can do pre- and post-processing directly on the platform with our desktops feature. In terms of security, this is our top priority at Rescale, and we have many security features built into the platform, which I'll come back to shortly. With our enterprise solution, we also have an administration portal that adds yet another layer of security to the platform. This allows IT and management to manage and monitor usage and to set additional budgets, permissions, and controls for users within their company. We can also integrate the platform with existing on-premise hardware, so IT and management can have transparency and control over all resources being utilized within their company. Coming back to hardware, as I mentioned, Rescale is a multi-cloud environment, and this span of infrastructure partnerships enables us to offer a wide range of different hardware configurations to our users. In addition to the 36 data centers, we also have 5 distinct sites, 2 platforms in the US, one of these being for ITAR-controlled work, and we also have dedicated platforms in Europe, Japan, and Korea. These dedicated sites are for users requiring that their data stay within one region. As I mentioned, security is paramount at Rescale. We go to great lengths and have many measures in place to ensure the platform is secure and that our users' information is protected at every step. We go through several in-depth processes, including audits, to meet strict security compliance and regulation requirements. One of the key security features we've put in place is encryption. Rescale's users' data is encrypted both in transit and at rest. And when simulations are running, they're run on isolated encrypted clusters. Should you want to have a more detailed security review, we're happy to schedule this offline with you. Now on to the partnership. NextLimit and Rescale formed a partnership back in 2014. This partnership has enabled both existing and new XFlow customers to both run their local licenses on Rescale and to purchase on-demand XFlow licensing directly on the Rescale platform. This allows them to instantly scale out their work. As Moyanto will show later, in addition to our straightforward workflow to execute your simulations, we also have our desktops feature available for pre- and post-processing that allows users to open up a remote desktop to visualize the results directly on the platform. We also have customized workflows available, including a DOE framework that Moyanto will highlight as well. Finally, should you run into any issues while working on the platform, we have a strong support team of cloud and CAE experts who are available to live chat and help with any issues users may have. Now I'm going to be passing this over to Rudy, who will introduce XFlow.
Thank you, Sarah. Okay, so hello everyone. Thank you for joining this webinar, and thank you, Sarah, for passing me the hand. So my name is Rudy. Indeed, I work as a lead application engineer at Nextme Technologies for XFlow. And so during this brief presentation, I would like to show you, well, a short introduction of XFlow itself as a method for people that may not know yet XFlow as a CFD tool, and also then for our customers, maybe also the improvements and new features we have in this latest version of XFlow 2016. And we'll then do a live demo of setting up a case of gearbox lubrication problem, and then I'll pass the hand to Mulyanto for running the job in Rescale, and he'll show you how to post-process and everything. So now let's start with the introduction of the XFlow methodology itself. Unlike a lot of CFD software in the market, XFlow is pretty different and has a very innovative approach because most traditional mesh-based CFD approach always face the same problems and bottlenecks, which are the mesh, the turbulence, and the numerical scheme. The mesh first because you know, when you want to work with complex geometries, mesh is always an issue, and you spend a lot of time trying to mesh complex geometry, and people need more and more to use complex geometries to model their problems. So that's a real bottleneck sometimes, and you have to remove some details of geometries for that. Also, the cells types have to be chosen according to the problem. You've got quads, triangles, and so on, so you have to get a good refinement and mesh strategy. Also, it affects the solution quality. That means that if your mesh is not good, your solution might not be good as well. So that's also a problem for that. And finally, all moving geometries are basically not straightforward at all to tackle with mesh-based simulations. So this is a bottleneck for all these problems here. Also, in terms of turbulence, most people rely on Rand's turbulence model. That's Reynolds average Navier-Stokes, and that's semi-empirical model, and that's not always appropriate to have a real good turbulence description of your problem and provides you only a mean solution, not, let's say, an unsteady solution of the flow. And LES is usually too expensive, as well as the DNS for finite volume method. Also, in terms of numerical schemes, Navier-Stokes equations are not trivial to discretize. That's a lot of problem, especially on the nonlinear advection term. You also need to add a lot of artificial viscosity to, let's say, achieve good stability of the solution and get a convergence, and that damps a lot of physics, of course. So the approach we propose is really getting through the limitations with a particle-based approach based on the lattice-Boltzmann method, which means no meshing process and easy handling complex geometries. Also, in terms of turbulence, we use LES turbulence model coupled with a wall function, which is a good accuracy turbulence model. And then we also get numerical scheme that is extremely easy to handle because of the lattice-Boltzmann method, which is numerically, let's say, much simpler than resolving the Navier-Stokes equations directly. So in terms of discretization, we do work with a sort of Cartesian lattice. That's called a lattice, and that's a Cartesian, let's say, mesh. And so what you get from that is that you get a grid like this of discrete points in space to discretize your geometries, like such NACA here could be discretized with that distribution of points here to get a good distribution of your fluid domain. And so that only requires a few inputs to generate that fluid domain. You need the geometries like this wing profile you see here. Then you need to specify only the resolution you want, for example, near the walls, far at the far field, and finally, eventually, also we have a dynamic wake refinement that allows, for example, to refine dynamically the wake as it develops, where you could specify also another resolution. With these 4 inputs, you just run the case, and the domain is generated automatically, so you don't have any issues dealing with that. And that allows a flexible refinement, adaptive refinement, and also an easy handling of moving geometries. As for the turbulence model, we use LES turbulence model, because for lattice-Boltzmann method, in fact, LES comes for free. It's a really low cost, and we can speak about 10 times less computation time for an equivalent simulation than with Navier-Stokes solver in terms of LES. So it's extremely, let's say, affordable. And that's why we go for an LES turbulence model. Meanwhile, the Ranswood model already scales of turbulence from the biggest one to the smallest one. LES will resolve the scales, and below a certain limit will model the smallest eddies. So in addition to that, we also use a wall function, that is the wall function you can see here, to model the boundary layer. Since the lattice is Cartesian, it would be extremely expensive to refine everything. So instead, we use a wall function that allows to get a good description of the separation near the walls, and also is in a good agreement with our turbulence model, LES. And finally, in terms of numerical schemes, so this is what I mentioned before. We use the lattice-Boltzmann method. The lattice-Boltzmann method is pretty different. It works on this very simple equation, which only has two terms. On the left, an advection term, streaming, and then on the right, a collision term. And this method allows you to very simply resolve the physics of the Navier-Stokes equation. So that works based on the statistical moments of the particle distribution F that you use and you integrate to get the macroscopic variables. This function F represents basically the distribution of particles in a given direction, in a given position at a given time. When you integrate those, you can get density, linear momentum, and those moments you can compute more moments to get more information. In addition, we use a very unique central moment space collision operator, which makes our lattice-Boltzmann approach also very special and offers a higher accuracy and lower numerical dissipation as well. So that was for brief introduction. Now I'll go very quick over the main features, new features of the XFlow 2016. So first of all, the multi-phase particle-based tracking. This is a new multi-phase solver that we developed. It's much faster, it's much more robust. It allows to compute basically two fluids, one liquid, one gas, or liquid-liquid, or gas-gas. But in a much more robust way than we used in our previous implementations. And that allows to do, for example, this kind of gearbox lubrication problems, and you get a real good tracking of the droplets all along the system. So it's very good when it deals with strong inertia forces and high density ratios, and can be employed for like gearbox lubrication, spray, splashing, tank sloshing, ship hydrodynamics, and a lot of different applications. We also have an improvement of the phase field solver that we made more robust. We ensured better mass conservation, and we improved the surface tension model also. And now it operates in a better way. And this is a model that is really dedicated for high surface tension effects, and when you've got relatively moderated viscosity and density ratios. So you can do a lot of different stuff like the bubble rise or this kind of microfluidics with also hysteresis effect that you could see on this video, which is basically imposing two angles, one advancing and one receding. So this is also a new feature. We also have a new coupled energy thermal model that is fully coupling or better coupling the energy and momentum equation, taking into account for mechanical work term, and allows, for example, to work on a compressions like the one you could see here, and works for subsonic isentropic flows. Also, we now can export the heat transfer coefficient either for a thermal analysis or an isothermal analysis. In case of thermal analysis, it's simply the definition of the heat transfer coefficient, which is a heat flux divided by the pressure gradient, the temperature gradient, sorry. And for the isothermal flow, we use such laws, which is based on the shear stress and pressures and so on. So also in terms of improvements, we have quite a few improvements. First, in terms of performance, because we optimized our code quite a lot. We worked on optimization. Now we've got a distinction between what are the bulk and the boundary lattice nodes, which are the one on the frontier, the borders, and the one that they are inside the fluid. And we made some enhancement for the bulk nodes. So these nodes that basically are computed much faster now. And we also improved the MPI scalability as well, doing an asynchronous MPI, okay, and dealing with this bulk at the MPI interface. So in the end, these results in up to 40% improvement in terms of computation time in XFlow 2016. And this is what we, for example, show in this external aerodynamics on this car. And this is a drive model that we use for validation, and results provided were exactly the same. The only difference was the computation time that you could see was lowered by 40%, going by about 80 hours to something in about 50 hours. So this is an extremely good enhancement for the performance. Also, in terms of supersonic solver, we get a better supersonic solvers, which is now called supersonic and not fully compressible anymore for more consistency. And we improved a lot of different things in this solver. Okay, more robustness. We cleaned it up, let's say, and now have better stability of the results. Now all pressures are defined in absolute values. Before it was in relative values. And so we are now a bit, let's say, able to validate much more simulations for supersonic flows. In terms of DPM, that's solid particles that you release into the flow. We also enhanced that feature. We can now, let's say, input more data, such as the distribution of different diameters as a log normal distribution. And you can also use a volume to initialize particles inside a volume. You can output data such as a particle distribution in the domain and leaving an outlet, for example. And you can also plot different things such as particles in function of their diameter and their ID as well. And finally, I think we've got the conjugate heat transfer model that has been improved. That means solid conduction is now happening let's say in a more straightforward way. The way to define the cases has been improved. You can now use as an external boundary the solids geometries to define a conjugate heat transfer. That wasn't the case before. And you can also apply some, let's say, thermal boundary conditions on these surfaces. We also improved our wall function, which is now based also with this Reynolds analogy, okay, with the formulation you can see here as well. So it allows now also to have better results for a larger range of Prandtl numbers. So this is it for this brief introduction to XFlow 2016. Now we'll go through a live demonstration. I'll do quick because I don't want to leave too little time for my colleagues from Rescale. And if you've got any questions, meanwhile, just contact us at XFlow, contact@nextimi.com, or go to our website, www.xflowcfd.com. So I'll jump now to my XFlow interface, and I'll do this gearbox simulation setup together with you on live, and then I'll pass the hand to Mulyanto for the rest of the analysis in Rescale. So this is the XFlow interface. For those who don't know, you can see that's different windows. You can see everything is very dynamic in XFlow. You can resize windows, you can move and fit windows wherever you'd like, toolbars as well. So it's extremely handy and easy to work with. And all the project is done in this single GUI, graphical interface. You don't have to open several interfaces, and we'll do all the setups through that. So all you do is you follow from left to right on the project tree. So let's get started. I'll start importing my geometries that are basically my gearbox and my box for the domain. I'm importing those two geometries. And now you can see these appeared in the center of my view, and I got these here. So we've got a box, which is this one, and you got a gearbox that is that one. So what we'll do is we'll do the setup now. So first the environment, that is the physics. So we'll do 3Ks, and this is going to be a multi-phase problem. So we've got different flow models, but that one is going to be a lubrication of oil over the gearbox, and we also want to take into account for air phase at the same time. And so you see now all you need to do is define a few parameters such as the gravity, which is already predefined since we are in a multi-phase, and it's in -y, so I don't have anything to change. My y direction will be my vertical direction, and also my gravity will be applied towards -y. I only have to set up this as an internal analysis because we see you've got a domain outside. So in this case, it's an internal case because we've got this box that defines the boundary of our domain, and we don't need to have any external domain in addition to that. So now we see only this box and this gearbox, and everything is all right. So now we can just define as an initial function the liquid where will be the oil initially. So you can define that with a load such as y is lower than 0.05 or -0.05, let's say, because I want to have, let's say, a quarter of my wheel to be covered with oil initially. So this would be about 1, 2, 3, 4, 5. So if I do y is less than -0.05, that means I will have initially oil in every region that's fulfill this condition, which means all this section here, which is what I want. Then we can define the materials. So let's say we've got two default materials, but I will just define oil in one case and give it some oil properties like 8049 km/meter cube as a density, and also 0.065, for example, for the dynamic viscosity. The default second material is air, and I will leave this as it is because I just will leave default air properties. Then I can also enable surface tension model and set, for example, 0.04 Newton per meter, which would stand for the oil-air surface tension. Now all I need to do is set my boundary conditions. So I will first locate slightly, move my domain, not my gear, but my domain, so that it is a bit above that. I don't want to have so much space in between the bottom surface and the gear, and also I'll center a bit my gear, oops, the other way around, like that, so that I've got more my shaft inside the domain. Now we're good, and this gearbox is going to rotate to make the, let's say, the oil initially on the bottom of the tank rotate around and speed around, and I'm going to move the behavior of this gear into an enforced motion. For that allows me to define some laws of position or angular laws, and in my case it's just a rotation around z-axis. You can see my z is in that direction. I could also choose a local axis, which is the blue axis is z, so I'm going to define, for example, 1000 RPM revolution per minute, but I need to define that as a function of degrees, which means 360 degrees for one revolution, and per second I will divide by 60. If I need multiply by t, this gives me my law in degrees, and so I've got 1000 RPM revolution per minute in that case. I can check the motion very simply. If I increase slightly my frequency because it's going to spin very quick, I can just play, and you can see these rotates around this axis. So that seems all right. We're happy with that, and we can go ahead on that motion. So that allows you to check beforehand how the motion will occur during the simulation. Now we're good. We've got our boundary conditions set. We just have to set a few simulation parameters. How much simulation time? I will do only 0.5 seconds. That stands for about 8 revolutions in that case for 1000 RPM. And that's probably enough to get most of my forces converge, the torque over the gearbox converge, and so on. I can also define a custom time step, and I will use, in that case, 110 -5, which basically for that case should be enough. So I'll explain now how I compute that, but I need to first define my resolve scale, which basically will be my lattice dimension and my resolution of simulation. How fine will be my simulation? In that case, we can see we've got a distance of approximately 1 centimeter in between the teeth. So what I'll do is I'll use a resolution of approximately 2 millimeters to get about 5 elements in between the teeth. That should be enough to at least get my first idea of simulation. And so now I've got my resolve scale defined, and I know my gearbox will have a tip velocity of 10 meters per second based on this radius. It's about 20 centimeter diameter and rotating at 1000 RPM. So if I do some computation, I can just compute that 2 to the -5 or 1 to the -5 should be enough to fulfill the CFL condition. Okay, so now I can just go forward, and I think I'm all done for my simulation, and all I need to do would be to run this on Rescale, of course, and take advantage of Rescale to run these jobs and do a DOE, for example, which I let Mulianto do for now. So, Sarah, if you can pass the hand to Mulianto, maybe?
Yes, I can. Thank you, Rudy. I am making the presentation now, Mulianto.
Okay, thank you, Rudy. I'm going to quickly show how to run the model that Rudy just showed on Rescale. So here you have the login page for Rescale. In this case, I'm running on our global platform at platform.rescale.com. We also have platforms in Europe, Japan, and Korea. So depending on what region of the world you are, you can run your jobs on a platform close to you. So I'll go ahead and log in. As far as logging goes, we support single sign-on as well as multi-factor authentication. But in this case, I don't have that set up, so I'll just have to enter in my password, and this will load the Rescale platform. So once the platform is loaded, you will be brought to the job list page, which lists all the jobs that are currently running or jobs that have already completed. You can manage your jobs here by either organizing them in folders or even deleting them or sharing them. So I'd first like to show you how to set up just a regular XFlow job on Rescale, and then I will show how to easily convert that into a parameter sweep using our DOE framework. So to start the job setup, I'll go to New Job here in the top left. And the first thing I'll do is give this job a name. And then I will go ahead and upload the files that I need for this job. And so what we need is the geometry files that Rudy showed, as well as the XFlow input file, the .xfp file. And we can select just all three of them. This will upload the files. In the top here, you can see the status of the upload. Once the files are uploaded, the bars turn green. If you've already uploaded your files earlier, you could alternatively select them from our cloud storage instead of uploading them. You do that by clicking this button here. And this allows you to select files that you've uploaded previously. Now that we've uploaded our files, it's time to go select our software. I'm going to click on the software icon here. and then search for XFlow, and then select XFlow. This will bring you to the software setup page. The first thing you can do is select a version. Of course, we're going to run the latest version. And the next thing you have to do is specify the commands you want to use to run your job. In this case, the command is XFlow and then the name of your input file. So let's go back and copy the input file name here. And we'll just paste it in here. And so this is the command that we're going to use to run the job. And then the last thing you have to do on this page is to select your license options. As Sarah mentioned before, we have XFlow available on demand. You can select on-demand licensing by selecting the purchase license checkbox here, which will give you an overview of the license pricing. Alternatively, you can bring your own license, and you would do that by selecting provide existing license. Here you would add the location of your license server. In our case, we're going to use the on-demand license, so we'll select purchase license. And then we're ready for the next step, which is selecting the hardware that you want to run on. So I'm going to click on the hardware icon here, which will bring us to the hardware configuration page. Here we can select the hardware configuration. We first have to select a core type, which is basically the processor and memory configuration that you want to use for your job. We have many different configurations available. Like Sarah mentioned before, we have GPUs, InfiniBand, and the latest Haswell processors. In this case, I will go ahead and run on the Onyx core type here, which are Haswell Xeon processors. You can specify the priority of your job depending on what priority you want to run your job at. You will have a different price for your hardware. In this case, I want to run my job as fast as possible, so I'll select instant. And the last thing I'll have to do here is select how many cores I want to run on. So let's run it on 72 cores. And then on the right-hand side, it will give you a short overview of the cluster that will be provisioned for this job. And so in this case, we'll run on 4 servers, and each server having 18 cores for a total of 72 cores. And above it, you have an overview of the memory storage of this cluster as well. So now we're ready to submit our job. So all I'll have to do is click the submit button. And this will go ahead and submit our job. So while we're here on the status page, I'll talk a little bit about the different status of your job. So the first status is validating input. Here we validate whether you have enough licenses or enough budget to run your job. Then we'll go ahead and start the cluster. Once the cluster started, it will start running your job. And then once your job is finished, we'll go ahead and shut down your cluster. On the top right, there's 2 buttons. One of them is the sharing button. This button allows you to share your job with either Rescale support, Next Limit support, or with a colleague. So for example, I can either share my support with Next Limit support, or I can, for example, share my job with Sarah, and then leave a message. When I share this job, Sarah will get an email with a link to the job, and she will be able to see what's going on with the job as well. The second button here is the clone button, and this will create an exact clone of your job setup, which is a useful feature if you run many similar cases, which will allow you to create an exact copy of your current job and just make small changes to the job and resubmit it. This is exactly what I'm going to do right now to show you how to easily convert this job into a parameter sweep using our DOE framework. So I'm going to go ahead and clone this job. And as you can see, we have an exact copy of the setup. My file's already loaded for this job. And so the first thing what I'll do is I'm going to convert this to a DOE job here in the top of the page. So I'm going to select DOE. Yes. And then the second thing I need to do is I need to templatize my input file. So I'm going to templatize this XFP file. So I'm going to remove that from my input files. And then I'm going to go to templates. And then I'm going to add this XFP file as a template. So now that I've added the file, I need to go ahead and templatize it. So I'm going to edit this file and find the value that I want to templatize. In this case, I'm going to templatize the viscosity of the oil. So here's my oil section right here. And here is the tag that I'm going to use for my template. So every value of my viscosity in my parameter sweep will be populated for this in this area, in this location here. So now that I've templatized my file, I will go ahead and specify the values for my for the parameter that I templatized just then, which is viscosity, and I'm going to do that in my parallel settings over here. I can either upload a CSV file with the values, or I can specify a range of values using the variable generator here. So I'm going to name my variable viscosity and set a minimum value, and then I'm going to set a maximum value and an increment. And so in this case, I will have 6 values for viscosity, ranging from 0.05 to 0.1, with an increment of 0.01. Lastly, what I want to do is set up post-processing. What this allows you to do is save output variables to the Rescale platform. What we've done is taken a script, a Python script, and this script will parse output variables from the output files that XFlow generates. So I'm going to upload my script, which I have here, and this script will then parse the variables out of the output files. And then I have to specify the command to run the script, which is basically just / and then the name of the script. So now we're all ready to submit a job. The difference between this job and the previous job is basically having set up a template, specified the variables to populate the template, and uploaded a script to parse out output variables for each run that we're going to run. And so in this case, we were going to run 6 different runs, 6 different runs for each value of viscosity. The last thing that we can do is update our hardware. We can actually go ahead and run this. For example, we can run all runs in parallel. So I can select 6 stash slots. And I can also, in this case, I'm just going to run each run on 18 cores only. And so all 6 runs will run in parallel. And now I'm ready to submit my job. Okay, so that's basically how you set up, a simple single run job as well as a parameter sweep job. I'm just going to quickly move to a already running job. So I kicked off the parameter sweep earlier before the webinar, and it's allowed to progress a little bit. And so this is what the status page looks like while your job is running. So in this case, the job has been running for 53 minutes. And on the left, you can see 6 runs that are running in parallel. And I can switch between all the runs. And each runs, when I select each one of the runs, it'll give you a list of all the files that are on the cluster. I can, for example, also filter the listing of files. For example, if I want to just see the logs, I can take a look at the XFlow log here, and which will give you an overview of how the run is progressing. Alternatively, if you have SSH set up, you can SSH into your cluster, and you can look at your files over SSH as well, if that's something that you prefer. Lastly, you can also monitor resource usage for the job, just to make sure that everything is going fine. You can look at memory, disk space, network traffic, etc. So that is what a job looks like while it's running. And the last thing that I want to show you is how to download your files once the job has finished. So here's a finished job. And when I click on this job, I get a table of all the runs for that job. And so in this case, I actually have 12 runs in this job. And I'll show you here the viscosity values that I used for my parameter sweep, as well as the output variables that I parsed out with my Python script. In this case, I parsed out the forces and the torque values for the gears, as well as for the overall forces in the system. I can also go ahead and visualize this data using our plotting functionality. For example, I can plot viscosity versus, say, the torque of the gear. And so that's the plotting functionality. So the last thing I want to show you real quick is, since we're running a little low on time, is how to use a desktop functionality to post-process XFlow jobs in the native XFlow graphical user interface. I do that by clicking on the desktops section here at the top. To launch a desktop, I could just click New Desktop. And I select the desktop that I want to use. In this case, I want to use a Windows GPU desktop.
All right, it looks like we're having some issues sharing our screen right now. So what we can do is send a short video demonstrating desktops as well following the webinar. Apologies for the delay on getting back to this. I'm going to try to share my screen right now. My screen. Looks like we're having some issues. So I'm going to jump to the questions. We had a handful of questions, and as we're rounding out the hour, I'm just going to address these now. One of the questions we received is, what is the difference between both multi-phase solvers of XFlow? I think this is a question Rudy can answer.
Yes, sir. Sorry, can you repeat the question again?
Sure. What is the difference between both multi-phase solvers of XFlow?
Yeah, sure. So we've got the particle-based tracking multi-phase solver. So as in the presentation, it's really good for high density ratios and strong inertial forces. And the other one, the phase field, is another formulation of multi-phase solver and would be better to tackle like small scales, low density and viscosity ratios, and let's say anything that relates to strong surface tension effects. So they are very complementary and resolves different physics.
Okay, great. Thank you, Rudy. And another question we had here is, can I bring my XFlow license onto Rescale? And we touched on this, but we didn't elaborate. In addition to on-demand licensing, we also have the ability to connect to your local licenses. As long as they're floating licenses from XFlow, you can connect and run those licenses to leverage the hardware that we have available. Because we are rounding out the hour, we have a couple other questions. I'm going to answer these. Rudy, Moyant, and I will answer these offline and email the individuals who ask these. As a final note here, all attendees today, doesn't look like my screen's sharing, all attendees today will receive $50 in Rescale hardware credit as well as XFlow trial evaluation license. So you can sign up for an account on the Rescale platform, it's just rescale.com, or you can contact sales@rescale.com to start a trial. We appreciate your time today. Apologies for the issues at the end with audio and connection here. Thank you, and if you have any questions, feel free to reach out to either Next Limit or to Rescale. Thank you, Rudy. Thank you, Moyanta, for your time.
Thank you, everyone.